definition, we tend to use to multiply the definition times u of n, the step function, minus u of capital N minus n. Okay, so you use this to say that you are multiplying the sequence times the step sequence. Okay. So in this way, everything else outside is 0. This is often we omit this because it's implicit in the DFT, but it's just a way to remind us that the DFT is 0 outside the interval between 0 and capital N minus 1. Okay, is it clear? If I'm forgetting something else. The DFS is just basically the repetition of the DFT, so I will not spend time on this. Okay, so now let me stop the sharing again. Stop sharing this. And let's start with what we'll talk today. And what I want to do today is to spend a little bit more time on this relationship between the DFT and the discrete time Fourier transform. So let me start the presentation. Okay. Okay. So you see my presentation? I hope yes. This is something that I shown already before that summarize the different Fourier transforms in the characteristics of the Fourier transforms and the signals in time and in frequency. And we have seen, or you should know already from previous courses that when you have a Fourier series of a continuous periodic signal, in frequency we obtain an infinite number of coefficients, of discrete coefficients of the Fourier series. In the continuous time Fourier transform, you have a continuous function that is in principle infinite, and in frequency, when you do the Fourier transform, you have a continuous function that is infinite as well. And then when you sample the signal and you have a sequence, a discrete infinite sequence, when you do the discrete time Fourier transform, what you obtain is a continuous function that is periodic. And we have seen this, that you have the periodic repetition of the spectrum. Okay. And then last time we have seen the discrete Fourier transform and this discrete Fourier series. And in time, these come from the discrete finite, sequence or a discrete periodic sequence, and they produce a discrete finite sequence or a periodic sequence, respectively. Okay. And this is, as I said, it can be seen also as a change of base, because you go from a discrete finite sequence to another discrete finite sequence of the same length, depending on the number of samples that you use for the DFT and the DFS. As a reminder, this is the definition of the discrete Fourier transform. Okay, it's the infinite summation of the sequence multiplied by e to the minus j omega n. Differently from the normal continuous time Fourier transform, this is an infinite summation and not an integral. And we don't use the frequency, but we use a discrete normalized frequency variable omega. Okay? So omega is not infinite, but it goes from 0 to 2 pi or from minus pi to pi. And the reason is that the DTFT is periodic. So it makes no sense to consider omega from minus infinite to plus infinite, but we only concentrate our attention on the main period that, as I said, can be from 0 to 2 pi or from minus pi to pi. Okay? The inverse discrete Fourier transform is some sort of Fourier synthesis, and this time it's an integral, it's not a summation, because the DFT is continuous. It's periodic, but it's a continuous function. So we have to do an integral, and the integral is, for example, here from minus pi to pi, normalized divided by 2 pi, and it's the integral of the DTFT multiplied by e to the j omega n in the omega. So we have a continuous periodic function, capital X of e to the j omega, and a discrete infinite sequence x of n. So the inverse discrete Fourier transform is actually a Fourier series analysis, except for the sign of omega. Is it clear? Again, this is something that we have seen already in the first lectures. Now the DFT, as I said, is a transformation from a discrete finite or periodic sequence to another discrete finite or periodic sequence. Okay? So since the periodic sequence, so for both finite or periodic sequence, we will only consider the distinct values, for example, capital N, if the length is capital, if the support is capital N, or if the main period is capital N. So the spectrum is completely defined by n distinct frequency samples. It makes no sense to have more than n, okay? Because you only have n samples, okay? So if we divide the interval between 0 to 2 pi in capital N equal steps, then the frequency samples are 2 pi over n. And basically the DFT is defined with this omega n, as I said, is e to the minus j 2 pi over n, and it represents 1 over n of the revolution of a circle, okay? And it's basically the roots of unity, the complex roots of 1, okay? And here you have the definition of the discrete Fourier transform and the inverse discrete Fourier transform. I will not spend much time because we have seen this last time, right? Any questions about this? Okay, so let's go on. And what we will see today is the relationship between the discrete Fourier transform and the DFT, and I will be a bit more mathematical than last time. Last time I was a bit descriptive. I was giving more the sense of what's going on, and now I will give you a more formal proof, okay? So if the sequence has finite length, the discrete Fourier transform is some sort of sampling of the DTFT as certain discrete frequencies. So here you have a plot where you have the DTFT in red which is periodic. You don't see here that it's periodic because we look only at the main period. And then the DFT is the samples of the DTFT every 2 pi k over capital N. Okay? Okay. So let's consider a limited support sequence, x of n, that is contained between 0 and capital N minus 1. Okay? So if it's a limited support sequence, of course, it will be summable. And since it's summable, we can compute the discrete time Fourier transform. And also, we can compute the discrete Fourier transform. Okay? So if we combine the definitions of the DTFT and the inverse DFT, what you obtain is here in the first equation. Okay? So you have a summation that is due to the discrete time Fourier transform, that it should be infinite. If you remember here, it should be an infinite summation, but because the sequence has a finite support, all the other elements are 0, so we consider the summation only from 0 to capital N minus 1. Okay? And the second summation comes from the inverse discrete Fourier transform. So in the inverse discrete Fourier transform, we have the samples of the DFT. Here it's written capital X of M. And then you have the coefficients of the inverse discrete Fourier transform. And then you have the components of the DTFT, which is e to the minus j 2 pi Fn. So F is the frequency, the normalized frequency that is continuous from 0 to 1, for example, or from minus 1/2 to 1/2. And then you have the coefficients or the sequence of the DFT, capital X of n. Okay. So let's go to the second part, the second equation. Sorry, there's a thunderstorm here in Palermo. So if we inverse the summation and we take the coefficients of the DFT outside, what is left in the internal summation? You have the summation of n that goes from 0 to capital N minus 1 of e to the j 2 pi m divided by capital N minus f times n. Okay, and this is a geometric progression, and you know that the result of this geometric progression is what you see here on the last equation above, is 1 minus e to the j 2 pi m divided by capital N minus f times n, and divided by 1 minus e to j 2 pi m divided by capital N minus f. Okay? So if you regroup half of these components, in particular if you regroup above e to the j pi m divided by capital N minus f times n, and below e to the j pi m divided by n capital N minus f, what you obtain if you use Euler's formulas is this last equation in the form sine divided by sine. Okay, and then you have the factor e to the j pi m divided by capital N minus f times n minus 1. The minus 1 is because of the denominator, okay? Is it clear for everybody? Yes?
Yes, sir.
Okay, if there are any questions, let me know. And if you use the angular frequency, omega, then it's a very simple transformation and you have the results here, okay? So what we obtain is basically that we can represent the discrete time Fourier transform x of e to the j omega as samples of the discrete Fourier transform. So as a summation or a combination of the discrete Fourier transform elements. Okay? So this is how we somehow mathematically reconstruct the DTFT from the samples of the DFT, okay, using this interpolation, sort of interpolation formula. So this form sine over sine is what we can call a periodic sink. It's not a sink that you are used to see in the continuous time, because it's in the form sine of capital Nx divided by sine x. And here, what you see in this plot, you see in green, at higher frequency, the function sine of capital Nx. And then you see in blue this lower function sine of x, okay? And if you consider the ratio between the two, you obtain this red function that looks like the sinc function, but with the difference that it's periodic, okay? So this is what I mean as interpolation by periodic sink, because all of the samples of the DFT are multiplied by periodic sink to reconstruct the discrete time Fourier transform. Okay, so the previous relationship between the DTFT and the DFT becomes 1 over capital N, and summation of the samples of the DFT, so x, capital X of k, multiplied with a periodic sink, which is a pure real function. And then there is a pure phase function, which is the one you see on the right. Okay? And these pure, these coefficients are equal to 0 every time there is this factor delta omega k, which is the difference between the angular frequency and 2 pi k divided by capital N. And so basically the multiplication factor of the coefficients is equal to plus or minus n when this factor is equal to 0 or pi divided by 2, and it's 0 every time delta omega k divided by 2 is a multiple of pi over capital N. Okay? So this comes from the periodic sink interpolation. So basically what you get is a sort of interpolation formula of the DTFT with the components of the discrete Fourier transform. Okay? Is it clear for everybody? Are there any questions, comments? Okay. So what happens if the sequence x of n has more than capital N points? Okay, this is a question that we ask ourselves. Of course, you can still sample the DTFT, so you can always construct the sequence x of k using the samples of 2 pi k over capital N. and we obtain a sequence x of k that is of capital N points, because we have only used capital N points. And this sequence will be periodic, because the DTFT, of course, is periodic. So if we compute the inverse discrete Fourier transform of capital X of k, we get a sequence of capital N points. But these capital N points probably are different from the original sequence x of n, because the original sequence had more than capital N points. So the question we want to answer is, how does the obtained sequence x tilde of n relate to the original sequence x of n? Okay. So here it's explained probably better in the slide. You have a sequence that goes from minus a to b in the support, I mean in the length of the sequence goes from minus a to b. We compute the DTFT, which will exist for sure because the sequence is limited, and the support of the sequence is limited, and so the sequence will be summable. So we can compute the DTFT. And then we sample the DTFT to obtain the sequence x of k. And then from the sequence x of k, we compute the inverse discrete Fourier transform x tilde of n, which has support from 0 to capital N, which in general is different from minus a to b. So the question is, what is the relationship between the two sequences, x and x tilde? No, il filtraggio è per ottenere quella continua, la funzione continua. Qua stiamo parlando di campioni, di sequenze. Non parliamo di Fourier transform. Okay? So I'm not speaking of the continuous time Fourier transform. We are not there yet. We're just looking at the discrete Fourier transform, discrete time Fourier transform and discrete Fourier transform. So we are using already the sampled signal x of n. It's a sequence of numbers. It's not a continuous function. All right? So here you have basically the solution of your answers, which a little bit we have seen last time. So we have x tilde of n. This is basically the two definitions. First, you have the definition of the inverse discrete Fourier transform. And inside, in the parentheses, you have the definition of the DTFT. And this is why you have the infinite summation from minus infinity to plus infinity. Okay? So, as I said, you can, as I showed you just before, you can take outside the infinite summation, and what is left inside is 1 over n, and then the summation of the Tweedle factors, Wn of k of times L minus n. And this summation, if n minus L or L minus n is the same, if this n minus L is a multiple of capital N, this will result to 1, okay? Because what you have is the summation of all the roots of unity, and if you sum them all, you have capital N, divided by capital N, it will be 1. Okay. Instead, if you have that n minus L is different than a multiple of n, then this summation will be 0. I don't know if it's evident. I can show you here, perhaps on the whiteboard. Let me share, let's see if I can share the screen like that. Okay, so let's see. Okay. So what I'm saying is that if you have the summation of the factor 1 over capital N, summation of Wn of k of L minus N, okay, you have this. Basically, what we're doing is that, what I'm saying is that if L minus N is a multiple of capital N, what you have here is e to the minus j 2 pi divided by n, and then here you have an, okay? So you have a multiple of 2 pi, and this will be always equal to 1, okay? So no matter what is k, here you will have 1 over n summation of 1, okay? And so this summation of 1 from 0 to n minus 1, okay, on n elements, this will be equal to capital N, and so this will be equal to 1, okay? Instead, if L minus n is different than a multiple of n, what you obtain is that you have the summation of all the roots of unity. So basically, you have, you know, the roots of unity. It can be, for example, this. This is for the roots of unity. And what happens is, if you sum all these in vector, what happens is that the result will be 0, okay? So basically, if you sum all these together, the result is 0. So if L minus n is different than a multiple of n, you have... no, non ho fatto niente ancora. So you have basically 1 over n times 0, that is 0, okay? So this is what I mean in this sense. Let me go back to the presentation. So here what you have is a factor that is 1 if L minus n is a multiple than capital N, otherwise it's 0, okay? So the result will be that we have the elements, the infinite summation of the sequence of X, but you have that L, compared to L, must be equal to n minus R capital N. So basically, only these elements will be inside of this summation. Otherwise, the other elements will be 0. And so what we obtain is that the sequence x tilde of n is equal to the original sequence x of n, but there will be also the replicas of the original sequence shifted by multiple of capital N. Okay? And so all these shifts will be inside the interval between 0 and capital N. because the sequence x tilde of n has limited support between 0 and then -1. Okay? So it's some sort of aliasing, some sort of repetition, but not on the infinite time, but only in the overlap in the interval 0 to capital N. So let me explain better in the next slide. Okay? So let's consider the sequence x of n that has these certain values of 8 points. Outside the interval between 0 and 7, the sequence is 0. Okay? So we form the sequence capital X of k, so the discrete Fourier transform, only on 4 points. We choose capital N equal to 4. So k goes from 0 to 3. Okay? And how we construct this sequence is sampling the continuous periodic DTFT in 4 points, which is 2 pi divided by k, divided by capital N times k. So we are sampling in only 4 points, which are 0, pi divided by 2, pi, and 3 pi divided by 2. Okay? So the inverse discrete Fourier transform of x of k will give us a sequence x tilde of k of only 4 points. Okay? And since there is only 4 points, in those 4 points there will be an overlap of the original sequence plus the periodic repetition for r equal to -1. So there is a repetition, but the repetition goes outside the interval of from 0 to 4, from 0 to 3, sorry. Okay? So you have the original points that are above, 8, 5, 4, 3, but also the shift, the sequence that is shifted by 4, but the shift is again inside the interval. So the elements will be summed with the values of 2, 2, 2, 1. So the result of x tilde will be the sum of these two. Okay? So we cannot reconstruct the original sequence x of n because since we have used only 4 points for the DFT, for sampling the discrete time Fourier transform, then the sequence that we obtain x tilde of n is the time aliased, or the folded version of x of n, on only 4 points. Okay, so what you see here in the plot, you have the original sequence. Then we want to build the x tilde, which is the sum of the original sequence plus the repetition shifted, and we take the points only from 0 to 3, and then we sum them together to obtain the x tilde function, which is the one that is at the bottom. Okay? Is it clear for everybody? Or are there any questions? So as I repeat, in the graph, on the top you have x, the original sequence x of n. The one in the center is x of n plus 4, so we shift by 4. And then the result at the bottom is x tilde of n, which is the sum of the repetition. Okay? In principle, it's not only this sum. In principle, there is an infinite sum of these sequences, but all the other points are 0. So even if they overlap, there is no contribution to this sum. So these are the only points that overlap in the sum, that have an impact on the sum. Okay. Clear now this formula x tilde is equal to the sum of the repetition, but only between 0 and capital N. So only from 0 and n minus 1 on n points. Okay. Okay. So incidentally, I want to talk about circular time shifts, which is something that I just shown now. So when you have a 5-point sequence and you are shifting by 2 points in on a 5-point sequence, when you have a delay by 2, what you have is that you have the last 2 points that go out from the right and go back in from the left. Okay, and this is sort of like a barrel shifter when that you delay the points in circle, not linearly. Okay, so this is a circular time shift. Is it clear? And you have to be careful, because when you do a circular time reversal, this is tricky when you do a circular time reversal, because the point in the middle doesn't change. The point in 0 does not change. So time reversal is not reversing the sequence when you're looking modulo n. So what you see in the top is the periodic sequence of 5 points. You do the repetition, but when you reverse it, when you reverse this sequence, what you see is all the other points changing except the point in 0. Okay, so the 0 point stays fixed and the other one turns around. So be careful when you do time reversal in modulo n. This is something that will be important later. Okay. Are there any questions up to now? If there are no questions, I suggest we take a 5 minutes break before we continue with the lectures, okay? So see you in 5 minutes. Okay, so let's go back to our lecture and let me share the screen again. Okay. Okay, so what I want to talk now is the linear convolution sum, but using discrete sequences. Okay, you are probably used to the convolution in continuous functions, right? With the integral. What you see here is the definition of the linear convolution, but on discrete sequences. Why it's important, the linear convolution? It's because when you have a signal that goes through a linear time invariant system, the output will be the equivalent of the convolution of the impulse response of the system with the original sequence. Here what you see is the output y of n, and you see the convolution of the input sequence x of k with the impulse response h of k. And you can look at on both sides. You can think of it as the sequence that goes through h, through the linear time invariant system, or since if the system is linear time invariant, you can invert and think of h that goes through x. Okay? So you can think of it in both directions. And let me say a word about the interpretation of the convolution. So we have the sequence x of k that I've shown you before, and we can look at as the convolution as h that is flipped. So here you have on the right you have x of k, and then you consider h that is flipped, so h of minus n, and then you have n that increases. So if n is 0, what you have is this h of minus k, or if you want, g of k. And it's the flipped version. So remember here, how was h? The values are 3, 2, 1, and then all the rest is 0. And then the first interpretation of the convolution is to flip in time h, and then you shift the function in time. Okay? So you have h of 0 minus k, h of 1 minus k, h of 2 minus k, and so on. And then you multiply these values with the values of x of k. So the result, each of the elements of the result, is the product of the first. For example, the first element is 0 because we have x of k that is 0 for k 0, and then you have for n 0, sorry. Then you have h that is not 0, but it's multiplied by 0. So the first element is 0. The second element is x of 1 time h of 1 minus k. Okay, so you shift by 1 on the right, h, and what you obtain, the value of 1 was 3, x of 1 is 3, h of 1, h of 0 is 3, so you shift by 1, and you have 3 times 3, so you have the first element, y of n is equal to 9. Okay. Then to compute the third element, you shift by one more, and you have the second element of x of k, and then again multiplied by h of 2 minus k. So you have 3 times 1, and then you have this the second, which is 2 times 1, if I'm not wrong. So you should obtain 1 again. You have 1, 3 times 2 is 6, and then you have, so you have 3 times 2, so you have 1 times 3 for the first, plus the second that overlaps, which is 3 times 2, and this is 6, so then you have 9, and so on. So every time it's more or less like the integral that you were doing in the linear convolution, but now you are shifting elements, so it's a discrete shift. Is it clear or not? Are you used to the continuous time convolution or not? Should I remind you how the continuous time convolution works? Maybe we should do this. Let me share the screen again. La convoluzione lineare la conosci, vero? La convoluzione lineare nel tempo continuo, se la ricorda. Sì. Okay, so what happens in the linear convolution in continuous time is that, for example, if you have the convolution of, sorry, why is not right? Okay. So if you have, for example, the linear convolution of this function with itself, what you do is that you flip over, this is not a good example, sorry, let me start again. So you have this with itself. If you do the convolution of these two, what happens? Let's give names. This is x, this is h. So in the first interpretation, you have that x here, and then here you flip h, okay? And then the result of the convolution is the integral of x and h, while h is moving this way, okay? So what you obtain, basically, while this is moving, is that, for example, you have moves like this, and the convolution is the integral of this part times this part, okay? So first you have something like this, and then the function h continues to move, and so the overlap is here until here, and so you have something that continues like this, and then when you go out from the other side, you have only this overlap here, for example, okay? And so then it goes down. So overall, this is what you obtain in the linear convolution. This you should know, right? Giusto? Okay. So now what happens in the linear convolution with discrete time signal is something similar, but instead of having the integral, you have the summation. So what you have is, let's say this. Okay, this is x of n, and this is x of t, for example. And here you have the same thing, h of n. And then, so you have the points, for example, like this. And then these points, they start moving in. And what you obtain here is the summation of the elements. So first you have, for example, only two elements overlapping. And here what you obtain is first 0 and then 1, for example. And then, as I showed before, you have more elements that overlap, and then you have this, and so on, and then it goes down, okay? Something like this. Because while you move, you overlap on more points, and then at the end, you don't overlap anymore. Is it clear for everybody? Is it clear? Okay, so this is something, this is what I mean here. Let me share the slides again. Okay. Sorry. Okay, so this is basically what is happening here. You have here this flipped sequence, H, that moves inside, and every time that moves inside, the overlap is higher, and so it goes up some sort of up, the convolution, and then afterwards, it goes out from the other side. There's no more points overlapping here, and so what you obtain is that it goes down, okay? Until it's zero because there's no more elements. So this is the first interpretation of the convolution. There is the time reverse of H shifted by n, and then you take the product of all the elements and you sum them all together, the inner product against x, okay? Now, the second interpretation of the convolution is that you are weighting the points of x by h, okay? So you're shifting x, you shift x, and all of these points are weighted by h. The result is always the same, but here you have h that is constant, and it's a weight of the shifted sequence x. Of course, you can define it the other way around. So you have the weighted delayed version of h, weighted with the points of x, is the same. Okay. The result, if there are no mistakes, it always has to be the same. So this is another interpretation of the linear convolution. Now let's see the periodic convolution. This is something a bit different. We consider two sequences that are periodic, x1 and x2, which have a discrete Fourier series, capital X1 and capital X2. Okay? And let's consider the product of the two DFS. So capital X tilde of 3 is the product of the two sequences of the DFS. So the periodic sequence with a given DFS can be written as the convolution, the periodic convolution of the two sequences. And of course, again, the periodic convolution is commutative, like in the linear convolution, okay? So this is how we define the two DFS in the periodic convolution. Now, if we substitute the periodic convolution inside the definition of the DFS, what we obtain is here the first equation. And if we interchange the summation, we take, for example, the one that does not depend on n outside, x1. Then the inner sum in the parentheses is the DFS, but with the shifted sequence. Okay? And you know from the properties of the DFS that the DFS of the shifted sequence is exactly the same DFS, but multiplied with a phase rotation of omega n of times km. Okay? So if you substitute this again back in the equation, what we obtain is the summation of the elements of the first sequence x1 times Wn of km multiplied by the DFS of x2. And this, what you get here, is the definition of the DFS of the first sequence. So what we obtain is exactly the multiplication of the two sequences. Okay? So, surprise, the convolution in time, the periodic convolution of the periodic sequences equals to the multiplication of the two DFS. Okay, are there any questions about this? So this is a graphical representation of the periodic convolution. You have here the two sequences, x1 and x2. Okay, x1 is basically a window that is repeated, and x2 is this function here that goes up and down. If you flip x2, what we obtain is this. Be careful, as I said, that the first point is fixed. Okay, when you flip, this doesn't change. Then you shift, for example, by 1. When you shift by 1, the first point moves here, and then this first element gets inside. Okay, and then here when you shift by 2, and so on. Okay, so this is the convolution is the result of this multiplication with this that is circularly shift. Okay, so the circular convolution of two finite length sequences is defined modulo capital N. Okay, so what goes outside from here goes inside on the other side. Okay, when you subtract, of course, you're going first you're flipping, but also the first element is fixed. Okay, be careful always to the first, so to the element in 0 that does not change, and then you move by 1, and then you go on and so forth. Okay, and then the result of the circular convolution is this one here. This is the result of the circular convolution, x3. Okay. Are there any questions about this? If there are any questions, let me know, please. Okay, so let's see an example. So to make it more easy to understand, let's consider the circular convolution of two rectangular pulses. Okay, so x1 and x2 are the same, are two sequences of length 6. So it's defined between 0 and capital N minus 1, and it's 1 here and 0 outside. The DFT of each sequence is the summation of 1, which is the value of the sequence, times e to the minus j to pi divided by capital N kn. Okay? And this, if k is equal to 0, is equal to n, because it's the summation of n times 1. Okay? Otherwise, if k is different than 0, this will be 0. Okay. If you don't believe me, you can do the geometric progression and do the computation yourself. But it's the summation of the roots of unity. Okay, so what we have seen before, and the summation is 0. The result is 0. Now, if we multiply the two DFT, what we obtain is n squared if k is equal to 0 or 0 otherwise. Okay. So the inverse DFT, of the multiplication, it will be 1 over n of what we have seen here, but with the plus, times n squared if k is equal to 0 or 0 otherwise. So it's only the first element, and the first element will be exactly n squared. So you have n squared divided by n, and the result is n. Otherwise, it's 0. Okay? And so what we obtain with the circular convolution is the same sequence, but times n. Is it clear for everybody? And this makes perfectly sense, because no matter how you shift this, is always 1 times 1, and you have n elements. So for all points here, you will have always n for the first, and for the second, and so on. Okay? Is it clear? Ok. Tutte le componenti. Tutti i punti. Okay, let's see another example. Okay. We increase the number of the samples to 12. Okay, it's the same sequence up to 6 points only, but the number of points of n is 0. Now what happens? The DFT of the sequence is this one here. Okay? And when you do the multiplication of the two DFTs, you obtain this. So now it's a bit different. Even if the sequences are the same, the periodic convolution is different, because this time when you flip the sequence, you have the first that stays where it is, but the other points are on this side. And when you multiply the first with this one, you have only 1. Then you shift by 1, or here you shift by 2 even. And what happens is that you have here 3 points, multiplied to these 3 points, and you have 3, which is this point here. And so on, until you shift by L. When you shift by L, you have the maximum, because you have these two overlapping completely, and it will be of height L. And then it goes down again up to 0. Okay? So here you have 6 points, but the number of points where you do the circular convolution is 12. It's 2 times. Okay? Now, does this convolution, this result, suggest anything to you? The solution. Okay, so here you have 2 rectangular sequences where you have a circular convolution that looks very much like the linear convolution. Okay. So we can do the linear convolution using the DFT. And the reason why we want to do this is that we have very efficient algorithm to compute the DFT of finite length, finite duration sequences. So computationally, it's very efficient to do the circular convolution instead of the linear convolution. Okay, So we compute the DFT of the two sequences on endpoints, we compute the product, and then we compute the inverse DFT instead of doing the convolution. But we have this problem that the multiplication of the DFTs does not correspond to the linear convolution, but to the circular convolution. To obtain the linear convolution, we must be sure that the circular convolution have the same effect of the linear convolution. Okay? So we must make, in sort, we will see this, I don't know if today or next time, that the two convolutions have the same effect. Okay. So let's consider now again the linear convolution of two finite length sequences. This is what we have explained just now. You have an infinite sum this time, and this time it's linear, so it's not circular. So if the two sequences are two rectangular sequences, what you obtain is this triangular sequence. And it's interesting to note that the length of the convolution is 2 times the length of L minus 1. In general, you have the sum of the two, the length of the convolution is the sum of the lengths of the two sequences minus 1, in general. In this case, they have the same length, so it's 2L minus 1. Okay? So when does the circular convolution act as a linear convolution? So we have the two rectangular sequences. If we use the circular convolution on the same number of points, we have aliasing in time. But if the number of points is higher, and in particular here you see the example of 2 times the length, you have no aliasing in time, and you obtain the same result of the linear convolution. Okay? It's not exactly Nyquist, because we're not talking about here there is no frequency involved. Here is just the length of the two sequences. Okay? It's not a matter of frequency, it's a matter of length. Let's see here another example. For example, here you have an example of a linear convolution of these two sequences. Okay? And the result of the linear convolution is of length L plus P minus 1, is what I said before. The first sequence has length L, the second sequence has length P, and the linear convolution has length L plus P minus 1. Okay? Is it clear? In the circular convolution now, what happens? Here you have the linear convolution result above, x3. The second graph is if we do the linear convolution on L points only. What happens is that the extra points, they overlap with the first part of the convolution. Okay? But if we increase the size of the circular convolution to L plus P minus 1, what we obtain is that only the zeros outside, they overlap to the sequence, and so the result is the same. Okay? There is no aliasing in time. Okay? Are there any questions, any comments about this? If there are no questions or comments, we can stop here for today. I will upload the slides on the Teams group, I will try to upload also the translation of the English translation of the lecture notes. In any case, you can look at the textbook, or you can try to translate the lecture notes from Italian yourself. And next lecture will be on Tuesday next week. Okay. Are there any questions, comments? Okay, so if there are no any questions, we can see you next week. Goodbye.